Hello, the project I'm doing is based on homework 614, that is to design a 10-bar truss. The following is the figure of the 10-bar truss problem. There are 8 forces and displacements. The length of each bar is 360 mm square, and the design variables are the area of each bar. There are two objective functions. The first is to minimize the total material volume of the bar, and the second is to minimize the maximum deflection of the bars. Notice, the second objective is not a continuous function, so I added 8 more constraints, each on each bar, and omitted the max function. There are 4 main constraints: stress, displacements, design variable, and buckling constraints. I will have 4 problems independently introduced later based on the objective function and constraints. The design of the problem will allow them to have different constraints based on different objective functions. This is the equation for buckling constraints that applied on the 5th and 6th bar. In design space exploration, there are 10 variables, so it is impossible to do a design space visualization with all of the variables together. I kept all the 9 variables the same value and increased one variable from low value to high value. Since the objective function is linear, we got the linear graph as shown on the right. The first optimization problem is to minimize the volume subject to stress, displacement, and design variable constraints. The solution is obtained by using F-min-Kong. Based on the Lagrange multiplier value, there are 4 active constraints. There are the tension constraints on x1, x9, x2, and compression constraints on x5 and x10. The result suggests that bar 4, 5, and 6 use the minimum cross-sectional area. The bar 1, 7, and 10 use almost the maximum allowable area. Other truss members are between 100 and 150 mm square. The second optimization problem is to minimize the maximum deflection of the truss while subject to stress, displacement, and design variable constraints. As we can see, other than bar 4, 5, and 6, other bars pretty much use the maximum allowable cross-sectional area. This is because the objective function is to minimize the maximum displacement of the bar. Increase the cross-sectional area of the bar will decrease the bar displacement. The third problem is to use multi-objective formulation to find the Pareto frontier while subject to stress, displacement, and design variable constraints. The following is the plot of the Pareto frontier. It is challenging because the inverse of the stiffness matrix is very nonlinear. Even compromise programming with a power of 8 is not working. I finally chose epsilon constraints method, but as we can see, it still has many dominated points, and that's the best I can get at this moment. The last problem is to minimize the volume of the truss. So I added a buckling constraint to the first design problem, and I assume the shape of the cross-sectional area is circular. So compare this result, which I listed at the end, to the first problem. We can see that almost all bars' cross-sectional areas increase. The active constraints are the maximum compression force displacement on the second bar, the maximum tension force displacement on the 10th bar, and the buckling on the 5th and 6th bar. Alright, that's all about my project. Feel free to give me some suggestions. Thanks.